Hi children, welcome. Welcome to another chemistry class. In this class, we are discussing hydrocarbons, the chapter hydrocarbons from the 11th standard topic. Let us straight away switch on to the questions. We are going to discuss some important questions from the hydrocarbons. All of you know it is dealing with the alkane, alkyne and benzene related molecules. Okay, the first question. In the reaction with HCl, an alkene reacts in accordance with the Markovnikov rule to give a product 1-chloro, 1-methyl cyclohexane. The possible alkene is 1-chloro, 1-methyl cyclohexane. Let us examine the first one treated with the HCl, Markovnikov addition. Cl minus will come here and H plus will be attached here. That means what you are going to get? You will be getting this one. 1-chloro, 1-methyl cyclohexane. So 1 is the answer. Second one. There is a combination, so I am checking the second one also. This is treated with HCl. So what will happen? Cl minus will come over this carbon, H plus will come over this carbon, Markovnikov rule. So the product will be same. Product will be same. It is 1-chloro, 1-methyl cyclohexane. What about the third one? Third one, it is not possible. Third one, it is not possible. It is going to be added over this region. Hydrogen will come here, chlorine will come here, or vice versa. Anyway, that is not going to give you the particular product. Answer is 1 and 2 combination. Fourth choice is the correct answer. Next. In pyrrole, electron density is maximum in. This is pyrrole. Suppose the pyrrole molecule is attacked by an electrophile. Where it will be attacked? It will be attacked mainly over these two regions. What is the doubt in that? Over the region 2 and 5. How can you understand that? How can you understand? You see the resonance structures of pyrrole. You see the resonance structures of pyrrole. There is a resonance as indicated here. You are getting plus and minus. Okay? And now a resonance. Switching further, you get a resonance structure like this, plus and minus here. Switching further, you get such a resonance like this, plus and minus here. Okay. So, how many resonance structures you've been able to get? One like this, one like this. So, it is 1, 2, 3, 4, 5 resonance structures you are getting. But I am sure all of you agree, this structure and this structure is most prominent, because the unlike charges must be very close. Here you can find the unlike charges are close, and that is relatively more contributing structure. You see plus minus charges far apart here and here. You see plus minus are far apart in these two structures. While here the plus minus characters are relatively close. So what is the rule governing the more contributing resonance structure? There are several rules you might have been taught. Maximum number of multiple bond, maximum number of pi bonds. That is one contribution, one rule. Pinenda, negative charge on more electronegative atom and positive charge on less electronegative atom. That is another one. Like charges are not too close, while unlike charges are not too far apart. Unlike charges are not too far apart. Here, the unlike charges are not too far apart. So, these two structures are more contributing structures, where you find a minus charge over this position and minus charge over this position. That means 2 and 5 will be more electron density region. Answer is second choice. Okay, next. Which of the following compounds shall not produce propene by the reaction with HBr followed by elimination, or directly only elimination reaction? Propene. First one definitely cannot. First one definitely cannot. Shall not produce. First choice. Because there is only 2 carbon. How can you get a propene? The reaction with HBr. How can that molecule give propene? Only 2 carbon atoms are there. While the others can be. There are 3 carbon, 3 carbon, 3 carbon. There are possibilities. First compound definitely not possible because it will contain only 2 carbon atoms. While you see second molecule, where is the second one, second molecule? This one, CS3, CS2, CS2Br. Upon elimination, you can get alkene. You can get alkene. This one with HBr, you can get this. Upon elimination, you can get propene. Propanol, HBr, followed by elimination, you can get propene. Propene. Then, here, if you take the first choice, if reacting with HBr, what probably can happen is you can get this, which upon tautomerization, you can get acetyl bromide. You can get acetyl bromide. So, all the other choices you are able to get propane except this one. So, first one is the correct answer. Don't have to analyze to that extent. First choice does not contain 3 carbon. That's enough. And ask for getting propene. Okay. Next. In the given reaction, the product P is first choice. Here there will be protonation. This will undergo protonation. This will undergo protonation as it is protic acid. And you will get a carbocation which will be attacking. You will get a carbocation which is attacked by the benzene ring. That is FC reaction. Friedel-Crafts alkylation reaction. That's all. Friedel-Crafts alkylation reaction. It's given there. You see, this upon protonation, you get a carbocation attacked by the benzene ring. You get a FC reaction, alkylation reaction, giving option 1. Okay. Next. The compound that will react most readily with the gaseous bromine has the formula. With the gaseous bromine has the formula. C4H10, that is an alkane. C2H4 is an alkene. C2H2 ethine. C3H6 propene. Answer could be the third one because alkane we rule out. This is alkane we rule out. Compared to alkene, alkyne we rule out because there is a symmetrical electron density present. Now there is ethene propene. Propene being an unsymmetric alkene will be more attacking compared to ethene. So the answer is third choice. Unsymmetrical alkenes are generally more reactive than symmetric alkenes. Unsymmetric alkenes are generally more reactive than symmetric alkenes. Okay. Next. Predict the correct intermediate and product in the following reaction. You are given with the propine undergoing hydration process. Propine undergoing hydration process. It will undergo a reaction according to Markovnikov of addition. You see the reaction? It's not given. I will write. See, propine interact with water. CH3, C triple bond CH with water in presence of sulfuric acid and mercuric salt. There will be Markovnikov addition. OH minus will come here and H plus will be coming here. You will be getting CH3, COH, double bond, CH2. Enol is obtained. Now further it undergo tautomerization. This hydrogen will come here and the double bond will come here. You get CH3, CO, CH3, acetone. Acetone. So what is the answer? Which choice? Option 4, isn't it? Option 4. Option 4. So please understand, suppose it was ethyne. Ethyne will give you ethanol. The hydration of ethyne will give you ethanol. Hydration of higher alkynes will give you ketones. Next. Which one is the correct order of acidity? Acidity is comparatively more in alkynes. The hydrogen with the triple bonded carbon, sp carbon, is relatively more acidic. So we are ruling out first choice and fourth choice. It can be second or third. Out of second or third, it is second choice. Because acidic hydrogen, 2 numbers, acidic hydrogen, 1 number, then alkene, then alkane. So when you compare the acidic nature of hydrogen, it is the hydrogen with the sp carbon more acidic than sp2 than sp3. Okay, yes. Next. The compound C7H8 undergo the following reaction. The product C is C7H8 with 3 chlorine. You get a compound, then it is interacting with the bromine ion. So first step reaction we can understand it is free radical reaction. Second step reaction it is electrophilic substitution reaction, while the last step is reduction. So what all things are happening there? You see, first step, it is free radical reaction and it will be attacking over the side chain. It is side chain free radical halogenation reaction. You can get CH2Cl, you can get CHCl2, you can get CCl3. So let us assume all hydrogen replaced. You are getting CCl3. Now we are conducting bromination. That is electrophilic substitution reaction. Now understand, the bromine will come here. Why? Why? That's the important point. CCl3, you see, this group is orthopara-directing, while this group is meta-directing. As there are 3 chlorine coming, that group turn meta-directive in nature. Okay, deactivating group, meta-directing group. So what happens? The new electrophile comes at a meta position. Bromine comes there. And now you are reducing. When you are reducing, this chlorine will be replaced with a hydrogen. And you are getting metabromotoluene. Metabromotoluene, third choice. So with the first reaction, when CH3 turns CCl3, the character also turns. CH3 if there, it is orthopara-directive. And CCl3 if it comes, it is meta-directing in nature. Next. Hydrocarbon A reacts with the bromine by substitution to form an alkyl bromide, which by Wood's reaction is converted to gaseous hydrocarbon containing less than 4 carbon atoms. A is. So among this you take one hydrocarbon, reacts with the bromine by substitution. So these two are out. They react with the bromine by addition. Alkene, alkyne react with the bromine by addition reaction. So out of 1 and 4. And now you get a alkyl bromide which undergo Wood's reaction giving less than 4 carbon atom. So the answer is 4. Suppose you take this. This will give you ethyl bromide, and ethyl bromide undergoing Wurtz reaction, you get butane, 4 carbon atom. We want less than 4 carbon atom. So what will happen? This is the answer. This undergoing bromination, you will be getting, just imagine CH3Br, which undergo Wurtz reaction, you will get, sorry, CH3, you get ethane, ethane. So the answer is fourth choice. Next. Which of the following carbocation expected to be most stable? What is doubt in it? These two you can eliminate because nitro group connected to the positive center. You know nitro group is electron withdrawing group. When nitro group is connected to positive center, the positive center will increase. Sorry. So 2 and 4 are least stable. What about 1 and 3? 1 is the answer because the positive center comes far away. The positive center comes far away. That's why. Okay. Here you have the highly electron withdrawing nitro group and the positive center is at a far position. So these two will be definitely unstable. Okay. Next question. The most suitable reagent for the conversion. You are given with 2-butene. 2-butene converted to cis-2-butene. 2-butene converted to cis-2-butene. Using Lindlar's catalyst, palladized charcoal with barium sulfate, quinol, sulfur, etc. Controlled reduction. Using Lindlar's catalyst, you will get stereo controlled product. You can get 2-butene converted to cis product, cis-2-butene. Suppose we are taking option A, you will get trans-2-butene. I am sure you learned about Birch reduction. This is called Birch reduction. Birch reduction. So choice 1, you will get cis product. Suppose it is choice 4, you will get trans product. Okay, next. Which is electrophilic substitution reaction? Electrophilic substitution reaction. First one is ESR reaction, where chlorine with AlCl3, you will get Cl plus attacked by benzene ring. Electrophilic substitution. This is free radical reaction. This is free radical reaction. This is nucleophilic substitution reaction. This is, I think all of you know, Sandmeyer's reaction. Very famous Sandmeyer's reaction. You are learning in the 12th standard topic. Sandmeyer's reaction. Very famous reaction. Sandmeyer's reaction also proceed via free radical mechanism. Okay. So the answer is first choice. Next. An alkene A on reaction with ozone and zinc water gives propanol and ethanol on equimolar ratio. It can't be ethanol. It may be ethanol. It can't be ethanol. It may be ethanol. Ethanol. Because Ozonolysis reaction provides a mixture of aldehyde ketone or same aldehyde, same ketone, or a mixture of the products, not alcohol. Addition of HCl to alkene A gives B as the major product. The structure of product B is. So, A on reaction with the reaction for ozonolysis, you are getting what? Propanol and ethanol. So, A undergoing ozonolysis, you are getting propanol. Propanol and ethanol. So what is A? That you identify first. How to identify A? You simply connect these two regions to get A. Remove that oxygen, connect with a double bond, you will get A. You see that CH3, C double bond, CH3, CH, CH3. This upon ozonolysis, you will get the corresponding propanol and ethanol. You see that this double bond will be broken and this part of the molecule will be converted to propanol and this part of the molecule will be converted to ethanol. Is that clear? Fine. So this is the alkene A. This is the alkene A. Now that alkene A treated with HCl, you get a B. This alkene, when treated with HCl, you will get a B. That is undergoing Markovnikov addition. You have H plus and Cl minus. Cl minus will come on this carbon and hydrogen will come on this carbon and the product B will be CH3, CCl, CH3, CH2, CH3. That is B. Asked for identifying what is B. The structure of product B is. Got it? Second choice. That is the answer. So from the ozonolysis product, identify what is alkene. And now take that alkene for Markovnikov addition to get the answer. Next. Same thing. Next. Which of the following alkane cannot be made in good yield by Woods reaction? All of you know Woods reaction is meant for producing even number of carbon atom. Alkane with a even number of carbon atom. Symmetrical higher alkanes. 2,3-dimethyl butane. That is a symmetrical higher alkane and you can produce. Cannot be. That is a question. Heptane. Heptane is the answer which you cannot. Because heptane is not a even number of carbon atom. You can get a butane, hexane. So these you can get. They are symmetrical even number carbon atom product. You can get by Woods reaction. Not heptane conveniently. Next. Answer is heptane. Next. Alkene on ozonolysis gives methanol as one product. Its structure is. See, if you take this for ozonolysis, it will break here. This carbon will become CHO and this carbon will become CHO. You don't get methanol. So that is out. Answer is B. Here it will break here and this carbon will be converted to HCHO, methanol. And the option B is the correct answer. Here also this carbon will be turning to CHO group. Here what will happen? It's breaking here. This is CHO and this is ethanol. You get ethanol and cyclohexane carbaldehyde. Answer is option B. Answer is option B. You will get one formaldehyde and one aldehyde over this region. Okay. B is the correct answer. Next. Product of the above reaction is alkylation reaction, FC alkylation reaction, you will get ethyl benzene. FC alkylation reaction, you will get ethyl benzene. This is attacked by AlCl3. You will get a carbocation which will be attacked by benzene ring and you will get ethyl benzene. The product is ethyl benzene. Option C. FC reaction, Friedel-Crafts alkylation reaction. Next. Electrophilic substitution, chlorination of methane, that is free radical substitution. This is free radical substitution. Addition of chlorine to ethene, that is electrophilic addition. This is electrophilic addition reaction. I want substitution. Benzene to chlorobenzene, that is the answer. Benzene to chlorobenzene with FeCl3. That is the electrophilic substitution reaction. What about last one? That is also addition reaction. Electrophilic addition reaction. So option C is the correct answer. Benzene converted to chlorobenzene. That is ESR reaction. The very famous reaction all of you learned. Next. Propine red hot iron tube. You get mesitylene. Ethine, you get benzene. Propine, you get mesitylene. It is not mesitylene. It is mesitylene. Mesitylene. This is what the reaction. Yeah, this is what the reaction. 3 molecules of propine will undergo cyclic trimerization. Cyclic trimerization. You will get mesitylene. Suppose you are dealing with the ethine, you will get benzene. Propine, you get mesitylene. Okay. Next. The similar reaction ethine given in the text. Similar reaction ethine given in the text. The same way it is propine. Next. A hydrocarbon takes up 10 times its volume of oxygen for complete combustion. The hydrocarbon is. Easily you can find out, no? Suppose it is propane. C3H8 plus oxygen. You get 3 carbon dioxide and 4H2O. 6 plus 4, 10. It will be 5 here. So option A is wrong. So simple cross verification, you will get your answer, right? And which one is the answer? It is heptine. Heptine. You see, heptine. There are 7 carbon atoms, 7 carbon dioxide, 12 hydrogen atoms, 6 H2O, 7 into 2, 14 oxygen, 20 oxygen, 10 oxygen. So it is option D. Option D. Try to check out how much it comes in octane, how much it comes in heptane. Try to check out. Next. Aromatic species is, this is anti-aromatic, that is non-aromatic. This is the answer. This is the answer, azulene. Azulene is aromatic in nature. Azulene is aromatic in nature. While A is anti-aromatic, B and D are non-aromatic because of the presence of sp3 carbon. Here you have sp3 carbon and it is non-aromatic, while this is maintaining 4n system. 4n system is cyclic planar conjugated 4n system is anti-aromatic. 4n plus 2 system is aromatic. Azulene is aromatic. So 7-membered positive center is aromatic, 5-membered negative center is also aromatic, and both refer to fused ring system, aromatic system. Okay. Yes. The 7-membered ring transfers 1 pi electron to 5-membered ring, and then both rings will have 6 pi electron, and the molecule becomes aromatic. Okay. Next. Allene is allene. This is allene. Allene is a cumulative diene. Cumulative diene is called allene. First one is a derivative of allene, but the compound allene is option D. Compound allene is option D. First one is derivative of allene. Next. Least readily nitrated. Least readily nitrated. Phenol, toluene, ethyl benzene, benzoic acid. Benzoic acid is least readily nitrated because of COOH group. COOH group is deactivating group. Here you have OH group in benzene, that is activating group. Here you have CH3 group in benzene, activating group. Here you have CH2, CH3 group in benzene, activating group. Here you have COOH group, that is deactivating group. Benzene with the COOH group, that is deactivating group. So that is less readily nitrated benzoic acid. Next. One mole HBr added to 1,3-butadiene, the product formed is 1 mole HBr added to 1,3-butadiene. This is 1,3-butadiene, and you are adding 1 mole HBr to this. You can get multiple products. There can be 1,2 addition, there can be 1,4 addition. There can be 1,2 addition, there can be 1,4 addition. Answer is A and B. What is happening here? Protonated. This is getting protonated. You get a carbocation like this, and you can get a carbocation like this by resonance. So you can get a carbocation like this and a carbocation like that. Resonance. And now bromine can come here and bromine can come here. So the answer is option D, A and B. 3-bromo 1-butane. This is 3-bromo 1-butane. Imagine bromine comes there. 1, 2, 3. 3-bromo 1-butane. And the other one is 1-bromo 2-butane. Bromine will come here. 1-bromo 2-butane. So you will get 2 products. Okay. So first product is 1,2 addition product. This is 1,2 addition product, while this is 1,4 addition product. So 1,3-butadiene with HBr, you can get 1,2 product and 1,4 product. Okay, next. The electrophile attacking benzene during sulphonation is. The electrophile attacking benzene during sulphonation is SO3. SO3 with the fuming sulfuric acid. When benzene react, you get benzene sulfonic acid. And the electrophile involved is SO3. Electrophile involved is SO3. I will write the reaction. You know that, but still. You see, benzene interacting with the fuming sulfuric acid. Benzene interacting with the fuming sulfuric acid. It will produce SO3. SO3 will attack over the benzene. And see what is the intermediate you are getting. What intermediate you are getting, you see? You get it like this. Now this releasing proton may be accepted there to get a final product, and the answer is the final product is benzene sulfonic acid. You get SO3H, benzene sulfonic acid. Looking at that, never try to comment C is the answer. The electrophile is SO3. Option B is the correct answer. Sometimes wrongly you may interpret looking at the product where you find HSO3 in the final product. It is not HSO3 plus which is the electrophile. SO3 is the electrophile. Okay, next. Addition of HCl to propene in presence of peroxide gives 1-chloropropane. 1-chloropropane. The reaction occurs through carbonium ion intermediate. Assertion is wrong. You don't get addition of HCl to propene in presence of peroxide gives 1-chloropropane. See, that statement is partially correct, partially wrong. Partially correct. See, you get 1-bromopropane, 1-chloropropane and 2-chloropropane. 2-chloropropane is the major product. If the intended product is major product is not 1-chloropropane. If that is the intention, the statement is wrong. Of course, you get 1-chloropropane and 2-chloropropane. The intended statement, if it is major product, that statement is wrong. That's what I said, 50-50, correct and wrong. Anyway, the answer given, if assertion, option D, assertion false, reason true. Okay, fine. So this is assigned to be wrong, this is true. Then we can attach here, gives 1-chloropropane as major product. Then that statement is wrong. The reaction occur through carbonium ion intermediate, definitely. Whether you make use of peroxide or not, I'm sure you remember anti-Markovnikov addition, that is peroxide effect, is observed only with the HBr. Peroxide effect is given only with the HBr, because free radical mechanism is initiated only with HBr, not with HCl. So whether peroxide is given or not, with HCl and propane, the reaction will be Markovnikov addition only, and the major product will be 2-chloropropane as the major product, and the reaction happening via carbocation mechanism. So second statement is correct, first statement is wrong, assuming that the intention for the statement is regarding major products. If you look at meticulously, without that, that statement can be 50-50, true and false. Okay. Next. So that's how the answer option D comes. Polynuclear arenes have the general formula CnH2n plus Y. The value of Y for anthracene is, this is anthracene, this is anthracene. You see the anthracene structure. And how many carbon atoms are there? 6, 12, 14 carbon atoms are there. There are 14 carbon atoms are there. And how many hydrogen? 1, 2, 3, 4, 5, 6, plus 4, 10. So 10 hydrogen atom. That means what is Y? C14. H 14 into 2, 28 minus 18 will be 10. So it is Y equal to 3. y is equal to 3. If you give y equal to 3, you will satisfy that formula. And you can have a shortcut. The number of ring, first ring, second ring, third ring, that is equal to y. The number of ring is equal to y. You can verify with other examples. Okay. Next. The product A is when the reaction conducted using Bayer's reagent. Bayer's reagent means, all of you know, cold dilute alkaline KMnO4 solution. Cold dilute alkaline KMnO4 solution. That is Bayer's reagent. That is Bayer's reagent. See, with the Bayer's reagent, there will be hydroxylation reaction. And you know the hydroxyl group will be added, syn addition. It will be syn addition. OH group will be added from the same site. And the answer is, this is anti-product, this is the syn product, option A. You will get cis product. You will get cis product. Cis hydroxylating agent. KMnO4 is a cis hydroxylating agent under usual scenario. So if you have an alkene in a plane, one OH, another OH will be added from the same side. It is cis product, syn addition. So Bayer's reagent is providing syn addition. While you remember, bromination is anti-addition. Bromination is anti-addition, while hydroxylation with the KMnO4 is syn addition. Next. The Newman projection formula of the compound given as, it is somewhat misplaced. Here it is Y, here it is H, here it is H. So I will draw a better one. It is X here, H, H. And Y here, H, H. That is the structure. The number of combinations of X and Y in which Gaussian form is more stable than anti-form. Gaussian form is more stable than anti-form. You see, my dear children, Gaussian form stabilizes. Gaussian form stabilizes when there is intramolecular hydrogen bonding. With the intramolecular hydrogen bonding, Gaussian form can stabilize. You might have seen some examples. Here imagine option A. Option A, suppose I am giving option A. That is, instead of X and Y, imagine I am giving CH3 here and OH here. You please try to understand, there is no possibility of hydrogen bonding. Between CH3 group and OH group, there is no hydrogen bonding. So option A is ruled out. Option A is ruled out. What about option B? Option B, I am giving OH here and F here. Definitely there can be hydrogen bonding. So option B can be the answer. Gaussian form will extra stabilize due to intramolecular hydrogen bonding if the combination coming is OH and F. The hydrogen of OH and fluorine can make intramolecular hydrogen bonding. So B is the answer. B is the answer. What about C? What about C? As far as C is concerned, there is NH2 group and OH group. Definitely there is a possibility. This hydrogen can interact with the nitrogen. So NH2 nitrogen and OH hydrogen can interact. Or NH2 hydrogen and OH oxygen can interact in hydrogen bonding. So that is also possible. So the answer is option D. Answer is option D. Both B and C, Gaussian form can stabilize. 29. The major product of reaction of 1 mole HBr with above compound is 1 mole HBr with above compound. HBr will be added over here. HBr will be added over here. According to Markovnikov rule. According to Markovnikov rule. How? Br minus will come here. H will come here. Option. Don't straight away select option A. It is option D. Option D. Because only 1 mole. So this is unaffected. This is unaffected. So it is option D. Option D. You get a carbocation there and Br minus will attack there. Option D. Simple. Markovnikov addition. Nothing. Don't confuse. That is not benzene ring. It is not benzene ring. Next. Identify the correct order of reactivity in electrophilic substitution reaction. Electrophilic substitution reaction. This is deactivating group, highly deactivating. So 4 is minimum. 4 minimum. So this is out. This is activating group. So 2 maximum. 4 minimum, 2 maximum. And the answer is option D. 2 maximum, then 1, then 3, then 4. You see, chlorine has got a speciality. Chlorine is at the same time deactivating, at the same time orthopara-directive. Chlorine performs, you have learnt, chlorine performs plus R effect and minus I effect. I effect is minus for chlorine and R effect is plus. So due to R effect, it is orthopara-directing. Due to I effect, it is deactivating group. Okay. So the order is nitro group, most deactivating, minimum, then 3, then 1, then 2, 2 maximum because CS3 group is activating group. Yes. And that was the last question from the concerned chapter, hydrocarbons. We will meet with another chapter in another class. Okay? Bye. See you.